I had no time to
recording.
Yes.
So the midterm grades were given to you, and 60% is a passing grade, and not many of you got that. So what do we do? Now, getting a passing grade is not an entitlement. You have to work for it. If some people could get 100%, you can also get 100%. So how do you study for exams? Number one, understand that no matter what you think, what you believe, all questions in all exams will always be from what we have done in class. There never was any question that has not been done in the class. Each and every question has been discussed in the class. If you think it hasn't been, then either you don't have the notes, you are absent, or you haven't studied it. But everything has been discussed in the class for each and every question. So keep that in mind when you study for your exam, that all the questions will be from what we do in class. I would suggest that you stop paying attention to those videos that you get online. Those are not meant for you. Those are meant for the layman. If you really want to understand, you need to study the book. You need to come to class, take notes, understand what we are doing. If you don't understand, you email me. But those generalized videos that you see on the internet, they are not going to help you. All right, so to help people who could not get a passing grade, so we can have extra quizzes, and that's what we will have. And one requirement for having the extra quiz, for doing that, is that you have to be here. So the attendance must be much more than what we have here today. Anyone who is interested in getting extra points to add to your midterm up to a passing grade. If you have already more than 60%, this does not help you. If you are less than 60%, you can raise it up to 60% at the rate of 1 percentage point for each right answer. So there will be 6 quizzes, and I emailed you the dates and the topics. 6 quizzes, 8 questions in each, 10 minutes.
6 quizzes, 8 questions.
And so that means, for example, if someone got, let's say, 50%, you have to raise it to 60%, so you have to get at least 10 questions right in all these 6 quizzes, which will be 6 times 8, 48 questions. So 10 out of 48 you have to get right, then you raise yourself to a passing grade. If you are scored maybe 20%, then you have to get 40 of them right to get up to 60%. And those who already have 60%, or those who take 1 or 2 quizzes and then reach 60%, if you want, you can stop taking the quizzes, or if you want, you can continue taking the quizzes, although they will not raise your grade, but that will certainly help you in studying or understanding, or maybe in the future board exam. I don't know what it will be good for, but knowledge is always good. So if anyone who already has more than 60% still want to take the quizzes, you are welcome to do so. If you don't want to, then you can leave at the end of the class. The class, of course, I will end at 10:40 or 11:40 as the day is, Tuesday or Thursday, and the quiz will be for 10 minutes after that. All right, so you have to be in the class to take the quiz. Any questions on that? All right, so we were doing citric acid cycle.
55 more, so slot 1.
And I had emailed you handouts like these showing all the steps in this. So we looked at the production of citrate. So I have to turn on the...
There's 4 quizzes, 8 questions each. I mean, you got the email, I didn't get the email.
Maybe I gotta lock in.
these are the same topics that were on the midterm.
Yeah, these are all midterm topics.
These are all midterm topics.
Because he's trying to test you on your midterm.
Oh, on the midterm itself. Oh, okay.
Say that someone has to be killed.
All right, so we were doing the citric acid cycle. So acetyl-CoA reacts with the oxaloacetate to give you acetyl-CoA as an intermediate, and then that acetyl-CoA is hydrolyzed to give citrate. So I explained why the acetyl-CoA is hydrolyzed, even though it's a high-energy compound, which you can use to get ATP, but the cell does not get that ATP because the concentration of oxaloacetate is very low. When the reactant concentration is very low, that cannot be an irreversible step. Because by definition, an irreversible step is one that has high reactant and low product. And so in order to push the reaction forward, the
I didn't say much.
coenzyme A is hydrolyzed so that delta G becomes negative, and that reaction actually is an irreversible reaction. So there are 3 irreversible reactions in citric acid cycle. This is the first one, and this is the first committed step. The other 2 irreversible steps are easy to spot because they have carbon dioxide release. Anytime you have a gaseous product release, obviously that is an irreversible step because the gas escapes. And so if the product escapes, that must be an irreversible step. So other 2 steps are those steps in which carbon dioxide is formed. Keep in mind the goal of citric acid cycle or any of these energy producing cycle is to produce energy or to make NADH, which is the reducing equivalent of energy, because it will be used to make ATP. And the other goal is to convert all the carbons of glucose to carbon dioxide. So because acetyl-CoA has 2 carbons, so there must be 2 steps in which carbon dioxide is released. Yes?
What is the first reversible step?
This one, the formation of citrate. Citric oxaloacetate plus acetyl-CoA, that is the first step. That is the first irreversible step and the first committed step. And once again, that is made irreversible by hydrolyzing the coenzyme A bond to it. And once you form the citrate, so this is citric acid or citrate. And as you see, this is not a chiral molecule, and the other thing you observe is that this is a quaternary alcohol. Sorry, this is a tertiary alcohol, so this carbon is a tertiary alcohol. And the goal of this cycle is to oxidize, and you cannot oxidize a tertiary alcohol. You oxidize alcohols to ketones, but this already has 4 bonds. You cannot oxidize to a ketone, and that's why the OH has to be moved from that position. And that's what happens in the next step. This OH is moved to this position, and that is isocitrate. Anytime you are moving a OH from one carbon to the next, we have seen that before in glycolysis also, it always goes through the intermediate in which you lose a molecule of water. So one hydrogen from here and OH will be lost to form a double bond. And then you add a molecule of water, and then when that water is added, the OH goes to the other carbon. So that's how all isomerases work. You're moving a OH from one carbon to another by forming a double bond, by removing the water and then adding a water. So that's what it does. In the book, you will find that intermediate also is drawn with a double bond here, but that is understood. The water will be lost and then water will be added, so the OH comes to this position.
There's nobody here today.
And this is isocitrate, which can be oxidized to form a ketone. And this enzyme is called aconitase. There are very few enzymes that don't tell what they do, right? As I said, enzymes are named based on the reactions they catalyze. This one doesn't, because this is named after the intermediate that I haven't drawn with the double bond between the two carbons that is called as aconitase. If you have an alkene here, that is an aconitase. Based on that, this enzyme is named, it's called aconitase, and that gives you isocitrate, and the purpose is that you want to oxidize the alcohol. Yes? Oh, yes, right. It has carboxylic acid on here.
He was going to test us about it.
So this is isocitrate. It will be oxidized to a ketone, and that again is an intermediate step in which you get this and 8 and all right, so this will be oxidized, and this is actually not seen. It is formed, but then it is immediately converted to the next one. And so in order to oxidize, remember the goal of citric acid cycle is to oxidize and release carbon dioxide. So for oxidation, you need NAD that will be converted to NADH. So you form one NADH here. Actually, that counts as 2 because glucose was converted to 2 3-carbon compound. And if you look at this one, this is an intermediate, and it has a alpha keto acid and a beta keto acid. So both alpha keto acid and a beta keto acid. So it is beta from alpha from here, carboxyl group, and keto at the alpha position. And if you look at this one, this is the carboxyl group, and then another carbon, then a ketone, so that is a beta keto acid also. And as I mentioned many times, alpha keto acids are difficult to decarboxylate, like pyruvate, and beta keto acids are easily decarboxylated. And so that's what happens. This is easily decarboxylated, and that's why you don't even see this intermediate. And so you move the double bond, the electrons here, and this bond breaks, and the electrons are absorbed by this oxygen. So that oxygen serves as the electron sink, and so you get this one. So this carbon dioxide is lost, and this is alpha keto glutarate. So one carbon dioxide is lost. I should write that. And that is another goal of the citric acid cycle, to convert the carbons of acetyl-CoA to carbon dioxide.
Why does that step involve NAD?
Because you are oxidizing this OH to a ketone. So you need an oxidizing agent. So there are usually 2 types of oxidation you will find in biochemistry. You are oxidizing an alcohol to a ketone, or you are oxidizing an alkane to an alkene. Yes?
And this is the second irreversible step?
Anytime you are forming carbon dioxide, that is an irreversible step. So this is the second irreversible step. And the product is a alpha keto acid, and alpha keto acids can also be decarboxylated, but it it will need a very huge complex of enzymes, just like the pyruvate was. And all the coenzymes that we studied there, they all work here, exactly the same mechanism. So you need the thymine pyrophosphate, and then the lipoamide, right, and then FAD, and then NAD. So all those steps with a huge complex that will decarboxylate this. And in the process, remember, from pyruvate, the product that you got was acetyl-CoA, right? So there is so much energy involved in the oxidation process that, first of all, you form NADH, which will later give you ATP. And still there is more energy, and that energy is used to form a high-energy compound of acetyl-CoA in the previous case. So in this case, it will be this remaining part. If you remove this remaining part will be attached to a CoA group. So this will then be coenzyme A here. Yes. So very similar reaction as with pyruvate. So pyruvate, along with all those complexes and lipoamide and thymine pyrophosphate, FAD, and then finally NAD. So in this case also finally it will be NAD, so you make another NAD. And this molecule, this is a 4, also keep track of the carbons. We started with oxaloacetate, which is C4, combined with two group carbons of acetyl-CoA, that makes it C6, and then you lost 2 carbon dioxide molecules, so you're back to C4. And your citric acid cycle starts with a C4 compound, which is oxaloacetate. So by the number of carbons, you are back to the right number. You just have to convert it to oxaloacetate. Yes.
And this is the third irreversible step.
This is the third irreversible step, yes, because carbon dioxide is released. And in case I forget, these are the steps that will be regulated, right? Regulation is always at the irreversible step, and these are the steps that will be regulated, and it will be by feedback inhibition. So what is the net product of all this whole thing? What is the goal here?
NADH.
But energy you are not getting right now. You are getting NADH, right? That is the product. Energy you will get later by oxidative phosphorylation. So the product is NADH. The other is carbon dioxide, which has already left the place. So the only product is NADH. So feedback inhibitor will be the NADH. So I won't remember. So this is the step. The first step is the citric formation of citrate before this, and then it is this step and this step that will be this step and this step that will be regulated. The 2 irreversible steps that will be regulated by NADH. So this one is a 4-carbon compound. This is called succinate, and it is attached to a coenzyme A. So this is succinyl-CoA, just like you had acetyl-CoA from pyruvate. And remember, this is a high-energy compound. It is supposed to give you ATP. It did not give you ATP with the acetyl-CoA because that reaction wasn't favorable, so you have to move that forward. But this one will give you ATP, right? Because you can hydrolyze this bond, and that will give you ATP. So let me just bring it back here. So in this process, ADP will be converted to ATP if you hydrolyze that bond. So the coenzyme A is released. So let me write with water. So you get OA, and that energy is used to make 1 ATP. So I wrote ATP here because many species make ATP. Humans actually make a GTP. So if you want to be really correct, this should be GTP and this should be GTP. But other species, bacteria, plants, they make ATP. So it's not important which high energy compound is made in the cell. They are all in equilibrium. ATP can be converted to GTP, GTP can be converted to ATP. It's not so important, but in case such a question ever arises, I never ask questions that require memorization. So I won't ask whether it's a GTP or ATP made. But you may see this question somewhere else. Remember, in humans, it is a GTP that is made. And that will give you succinate. Which is a 5-carbon compound. And so now the rest of the steps must be to convert this to oxaloacetate. Yes?
There's only 4 carbons in the succinate.
Yeah, succinate is 4 carbon.
Oh, okay.
So we lost 2 carbons as carbon dioxide, so we are back to 4 carbon. And the rest of the steps will be to convert succinate to oxaloacetate, and that way you complete the cycle. So in order to do that, you again need to oxidize this. And this is a different type of oxidation. There is no OH group here, but there are hydrogens. And you can remove 2 hydrogens to make an alkene that is also oxidation. As I said, in biochemistry, you will find 2 types of oxidation where you convert alcohol to ketone or convert alkane to alkenes. So this is the next step where you are making an alkene. That means a double bond here. And that involves less energy than oxidation of alcohols. So always remember, oxidation of alkanes require less energy than oxidation of alcohols. So amount of ATP you are going to get from this reaction, not now but later, will also be less. And that means the coenzyme will also be different. And that coenzyme is a new one. It is called Q. Q stands for coenzyme Q, also called CoQ, also called ubiquinone. They're all the same thing. Ubiquinone, the term ubiquinone comes from the fact that it is present in all cells. So ubiquinone, Q, CoQ, coenzyme Q, they're all the same thing. And this is a new coenzyme that we are studying. I'm not going to draw the whole structure of coenzyme Q, but there are 2 features in coenzyme Q that you should know. One is a quinone. There are many quinones that are present in various reactions, in not just this reaction, other reactions also. So there are other groups here which I'm not drawing. So this is one feature of a quinone, that when they are reduced, they will become alcohols. So this part will become OH here and OH here, and this will be aromatic. So when it is reduced, it becomes phenol or diol, triphenol. So this is the reduced form of Q, and as you see, it requires 2 hydrogens. So if this is Q, then this is QH2. So that's how it is always written. Q becomes QH2. So as I said, whenever you're removing 2 hydrogens, that requires less energy, and that gives you QH2. Obviously, just like NADH, QH2 will also be oxidized later to give you ATP, and it will give you less ATP than NADH. To give you the numbers, NADH gives you 2.5 ATP per NADH, and QH2 gives you 1.5 ATP per NADH. for a QH2. So you get less ATP made because it involves less energy. There is another feature in the structure. I'm not drawing the whole structure, but there is another feature like this. This is about, which is about 6 or so. So this group is repeated 6 times as a polymer. All right, so you can find this structure numerous times in the cell. If you want to look at it more carefully, it is a Y-shaped molecule, and it is called isoprene. So I'm going to erase the top part here. So this is 5 carbons, so it is isopentene. And this molecule is polymerized many times to make a long chain. And this is the starting material for making all the steroids, cholesterol also, and all of the steroid hormones. They are all made from this starting material. And this structure you will find often in other molecules also, because this is the starting material that comes from lipids. And that's why all the steroids are also called lipids, because they are derived from this. So this structure you see repeated a couple of times in this Q, and what kind of property will it give to Q? It is very hydrophobic, right? There are no polar groups there, only carbons and hydrogens. So that makes it hydrophobic, and that's why this coenzyme is present in the membrane. Alright, the NADH is present in the cytosol, or if it is happening in the mitochondria like this one, then it is in the mitochondrial matrix. Whereas the QH2 is present in the mitochondrial membrane. We will talk about the mitochondrial membrane later after this in oxidative phosphorylation. So just remember that QH2 is in the membrane, and this enzyme, where you are removing 2 hydrogens from succinate, the enzyme is called succinate dehydrogenase, is the only enzyme of the citric acid cycle that is present in the membrane. And this is the only enzyme that is also part of what is called the electron transport chain that we are going to study next, where ATP is made. So there are certain complexes that together make ATP by oxidizing NADH and QH2 and so on. And this is the only enzyme that is common between citric acid cycle and the oxidative phosphorylation that is done to make ATP, which we are going to study later. Alright, so that's one point. To remember first the structure quinone, then its solubility in the membrane. Whenever you are forming an alkene, the coenzyme is Q. And if you are forming an alkene from your organic chemistry, you know, whenever you form a double bond, there will be the question of cis and trans, right? So that question is always there in a test tube. When you're doing the reaction in a test tube, that question doesn't apply to the cell. Whenever cells make any molecule that can exist as 2 isomers, it will make only one of them. It makes the one that it needs and doesn't make the other one. And this is what was not understood before, and that's why they kept changing the name of this citric acid cycle also. So the enzymes themselves are chiral. They hold on to a molecule from one side only. And that's why you get only one of the isomers, whether it is enantiomer or diastereomer or geometric isomer, it doesn't matter. Your end product will be only one product in 100% yield because the enzyme itself is chiral. It allows whether it is adding or removing something from one side of the molecule. And that's why this will give you the trans product only, and that is called fumarate. fumarate is by definition the trans alkene with this structure. The cis one doesn't say this.
Just in this instance, it's trans. It's not the cell always makes trans.
No, in this input, whatever it needs, it makes that. For example, when we study lipids, we will see all lipids are always cis. So in those cases, it will always make only the cis. All right, so this one then, the next step is adding a molecule of water. So when you add a molecule of water, that means you're adding hydrogen to one and OH to the other. And again, same question arises, which carbon gets the OH? Does it really matter? From your organic chemistry, both the carbons are the same, right? This one or this one. But which direction will the OH come from? Because it will be a chiral center, again you are going to get D and L. But as I said, nature only makes only one of them, so you will only get the L malate. So you are going to add water to this, and so you get malate. So this enzyme is called fumarase, again another name based on fumarate. You are hydrolyzing, you are adding water to fumarate to get malate. And then the next step will be to oxidize this alcohol to a ketone. And once again, you will need NAD for this reaction. And these are all equilibrium steps, not irreversible steps. As I said, there are only 3 irreversible steps there. So this will oxidize this one, and that gives you oxaloacetate. That's what you started with. So you started with oxaloacetate, and then you're back to that, so that completes the cycle. There is one problem with this last reaction. This last reaction has a delta G equal to plus 30 kilojoules per mole. Right? That is delta G 0 prime. The standard free energy is plus 30 kilojoules per mole. So obviously that reaction is not a very feasible reaction thermodynamically. And so the cell has to make this feasible. That question arises for all cyclic pathways. If you are starting with a large amount of something, and then there will be irreversible steps where the product will be less than the reactant. And then you may get other steps, and then another one, if it is irreversible, then you must get a smaller amount of that. So eventually you end up with a small amount. Right, whatever the cyclic pathway is, the product keeps on getting less and less because there are irreversible steps in the pathway. So when you start the cycle again, you are obviously starting with a small amount, and how will you get a large amount of that? That is, so that question always arises for all cyclic pathway. The last one will not be a very feasible reaction, or the one before that. So one of the steps will not be a feasible reaction. And in this case, it is this one with a 30 kilojoules per mole. And so what the cell does is that we have started this, as I mentioned before, the citric acid cycle starts with a low concentration of oxaloacetate. And that's why the first one, we have to sacrifice the coenzyme A. So that is this last step of the citric acid cycle is the step before the first step of the next cycle, right? So in this case, the oxaloacetate concentration is very low concentration. By maintaining a very low concentration, you are making the delta G negative or possible, slightly negative or negative, because that is an equilibrium step. So you have to make sure that the delta G, actual delta G goes down to negative number starting from this plus 30, and that you do by having a oxalo acetate concentration very low compared to the malate concentration. But if your oxalo acetate concentration is very low, how do you start the next cycle? You start it by sacrificing that coenzyme A. And that's why you did not make ATP in the first step. Because the acetyl-CoA comes with energy. It already has the built-in energy in the coenzyme A bond, and that energy is used to drive the reaction forward, and that's why you don't make an ATP, because the oxalo acetate concentration to begin with is very low.
So he said to make the energy favorable, which one was lower than the other one?
The oxaloacetate, the very last step, is very, very low. So that, and when it goes back to the first step of the citric acid cycle, you're hydrolyzing the CoA,
To get that
the
energy
bond,
back.
to get that energy bond to
All right, so
add hydrogen
whenever
to
we talk about any pathway, we will end it by talking about regulation, but I already mentioned that. It will be regulated at the three reversible steps by NADH, the total end product of this, and that will be feedback in. There is another thing to study.
You're an amazing person, Anton, and I love you so much.
Cycle that is called the Lyell-Lake pathway. The glyoxylate pathway is not even present in humans, so why do you want to study it?
What is that glyoxylate?
Present in lower organisms, in plants, but humans don't have it. But we want to study it because people have the misunderstanding, or people tell other people that you can convert lipids to glucose, which you cannot. And this is a pathway that converts lipids to glucose in lower organisms. So we saw in the citric acid cycle that acetyl-CoA enters the cycle and 2 carbons are released as carbon dioxide. So if they are released as carbon dioxide, then you cannot make glucose, they are all gone. Right? All the carbons of fat are converted to acetyl-CoA, and then when it enters the citric acid cycle, it comes out as carbon dioxide, so you cannot convert lipids to glucose. The body needs glucose. A certain amount of glucose is absolutely necessary for you to survive, because some cells survive on glucose. For some of the brain cells need glucose and they work only on glucose, and other larger molecules don't even enter those brain cells. And so you need certain amount of glucose, which is probably around 50 grams or so. And so where do you get that? All those people who are on diet, and nowadays there are so many diets that try to cut down on carbohydrate, but don't cut it down to zero. Because a certain amount of glucose you always need, and you cannot get it from lipids. So what will you get it from then? If you're not taking in carbohydrate, lipids cannot be converted to glucose. So where will you get your glucose? You cannot survive without that glucose. So obviously your proteins will be broken down, right? So if you are eating enough protein, that is again okay. But if you are not eating proteins also, then obviously your muscles will be broken down to make that minimum required glucose for the brain. And that is done by gluconeogenesis, of course. So what are the precursors of gluconeogenesis? One precursor we saw is oxaloacetate, right? You convert pyruvate to oxaloacetate. And because oxaloacetate is a precursor, that automatically means that all the intermediates of the citric acid cycle are also precursors, because they can be all converted to oxaloacetate. So you take any of these that we have studied, succinate, malate, oxaloacetate, alpha-ketoglutarate, they are all precursors of gluconeogenesis. So any pathway that feeds into the citric acid cycle will help you to make glucose. But it cannot be acetyl-CoA, because both the carbons of that are released as carbon dioxide. It can be anything else that makes an extra molecule of these intermediates of the citric acid cycle. So how do plants do it? Plants, of course, you understand, they need this alternative pathway called the glyoxylate pathway, because when you plant seeds, the seeds germinate and they grow. They are not doing any photosynthesis. They are just starting from a seed to a plant. There is no chlorophyll, so they are not doing any photosynthesis. So how do they survive? They survive based on the lipids and carbohydrates that are in the seeds. And that's because they can convert their acetyl-CoA to glucose. And how do you do that? You have to bypass these two steps in which carbon dioxide is formed in the citric acid cycle. There are two steps, the isocitrate and alpha-ketoglutarate. They are decarboxylated. If you can bypass those two steps, then you can make one extra molecule of malate or oxaloacetate from the acetyl-CoA. So the glyoxylate pathway has all the same enzymes as the citric acid cycle. So you have acetyl-CoA, which is a C2 compound combining with a oxaloacetate, which is a C4 compound, and that together gives you citrate, which is a C6 compound. And then, of course, isocitrate, which is also C6, just the OH moved to another carbon. And these are the steps in which you are forming carbon dioxide. Red citrate, isocitrate, then two carbon dioxide molecules are formed. And the plants and bacteria, they can convert acetyl-CoA to glucose because they have another pathway that bypasses these two steps. So that means you are not converting the acetyl-CoA to carbon dioxide. Instead, isocitrate is converted to another molecule of, so it's converted to succinate. So, that's not right. It goes to the next step, not succinyl-CoA, but succinate. So after the succinyl-CoA, the next step is succinate. And remember here, one GTP is made. So the isocitrate is directly converted to succinate. So the succinate is a C4 compound, and the remaining two carbons are converted to a molecule called glyoxylate, which is a C2 compound. So instead of converting them to carbon dioxide, it is making it into a two-carbon compound called glyoxylate, and a four-carbon compound called succinate, which is of course one of the intermediates of the citric acid cycle. So citric acid cycle can continue from here to fumarate, and then to malate, and then to oxaloacetate. So citric acid cycle can continue, but you have a two-carbon compound called glyoxylate, which you haven't converted to carbon dioxide, and this glyoxylate combines with another acetyl-CoA, which is again C2. So this C2 and this C2 combines to form a malate. So that means you are forming two malates. One is coming from the regular pathway, this way, and another one coming from C2 and another acetyl-CoA to give you malate. That means you have one extra malate, and so that will make one extra oxaloacetate, and that will be used to make by gluconeogenesis. So that's how plants and lower organisms are able to convert their fat into glucose, but humans not, because we don't have this pathway to bypass the two steps. Yes, there was behind you. Yes.
What does it say in the middle?
Glyoxylate. That's the name of the pathway is also glyoxylate pathway, and this is glyoxylate. Glyoxylate has this formula. So glyoxylate is a 2-carbon compound. So instead of releasing 2 carbon dioxide molecules, you are have a 2-carbon compound that combined with another acetyl-CoA to make a 4-carbon compound.
And then before the malate turns into glucose, it turns into oxaloacetate again.
It's the same reaction. I should follow it. Let me write it this way. So this will convert to glucose. Right? So one oxaloacetate goes and continues the citric acid cycle, and the other one gives you glucose. So malate you will get 2, oxaloacetate you get 2. Right? One is coming directly, the other is coming from these acetyl-CoA. Alright, so oxaloacetate was the starting material for gluconeogenesis, so that's how you make glucose. So any intermediate of the citric acid cycle, if you have that in one extra amount, that can be used to make glucose, and that's how the lower organisms make glucose. Alright, so after you make all these NADH and H2, these will be oxidized. Oxidized by reacting with oxygen, and that's why it's called the oxidative phosphorylation to make ATP. So there are 2 ways of making ATP. One is by reacting with oxygen, and another is by using energy from a high energy compound to make ATP. So in glycolysis, you make 2 ATPs. That was from the high energy compound, 3-phosphoglycerine. And in the citric acid cycle, again, you make 2 ATPs from the succinyl-CoA. Remember, we are multiplying everything by 2 because it came from a glucose molecule. Based on 1 glucose gives you 2 ATP by glycolysis and 2 ATP in citric acid cycle. So you made 4 ATPs total going out this.
Where are you in the glyoxylate cycle? Where are you putting the acetyl-CoA that interacts with the glyoxylate? Like, where does it come from?
We haven't studied that. When fats are broken down, we will study that in later chapters. So fats are broken down by multiple steps, and at the end you get acetyl-CoA. So acetyl-CoA can come from at least 3 sources. One is from glucose, as we saw before. Other is from fat, and then the other one is from protein. Some proteins also give you, some amino acids give you acetyl-CoA as the end product.
And does this happen in the mitochondria or like
The fatty acid degradation,
just like the glyoxylate pathway?
glycolate is in the mitochondria. All right, so there are 2 ways of making ATP. One is substrate level phosphorylation, where you use a high energy compound. So we already got 4 ATPs by substrate level phosphorylation. And the remaining ATPs you are going to get by oxidation of all the NADH and QH2. So let's do some math here. How many NADH did we make? So glycolysis gave you 2 ATP in one of the steps, plus it gives you 1 NADH, or 2 NADH, because we are multiplying everything by 2. So how many ATPs will that make? When the NADH is oxidized, I mentioned that it gives you 2.5 ATP. So that will give you 7 ATP coming from glycolysis. So it's not directly coming from glycolysis, it's coming after, but at the end we are going to get 7. And then the citric acid cycle, that made 2 ATP right here in this equivalent. This is GTP, but equivalent to ATP. So 2 ATP you get here, and you made 6 NADH. There are 3 steps in which NADH was used. One was right here, and then here, and then this last step here. So 3 steps make NADH, so that makes 6 NADH. and there was one step where you made, from here to here, you made QH2. So that gives you 2 QH2s. So how many is that now? Need a calculator?
It's 1.5 per Q.
Oh, it's 1.5. It's
1.5
not
per
2.
Q. Yeah, so it's 3 and 12.
All right, so that makes it 6 times 2.5, so that's 15, plus 3 from here, that's 17,
6 times 2.5.
20, right? So that makes it 20 ATP from the citric acid cycle. And we forgot one more. From the glycolysis, you make pyruvate, that gives you acetyl-CoA. Right, that step gives you 1 NADH, 2 NADH.
What?
So 2 NADH you make in this step, so that makes it 5 ATP. So 7 is coming from glycolysis, 2 coming from the pyruvate dehydrogenase complex, and 20 comes from citric acid cycle, so that makes it 32 ATP. So 32 ATP per glucose. So oxidation, complete oxidation of glucose will give you 32 ATPs. And this number, you will see that it doesn't agree in all books. People write whatever they want. Right? So one number you will find is 38 or other numbers, but this is the number. Trust me, right? 32 ATP you get. So why do people have different numbers for this? There was a time when the different numbers were justified, but now it is not. One number is 38, that is frequently written in some books, and that's because people did not understand how you can get fraction of ATP from a chemical reaction. QH2 gives you 1.5, NADH gives you 2.5. Where are these fractions coming from? In chemistry, you know you balance equation, you have whole numbers, you don't have fractions. And that's why people thought this must be 3 and QH2 must be 2, and that gives you different numbers. So why are there fractions? When you balance an equation, you don't write fractions, but here there are fractions getting in it of ATP made. And as we will see in this oxidative phosphorylation, that ATP is not the smallest currency of energy. As we mentioned before, all your energy is coming from ATP, and whatever you need energy from will be from ATP. But ATP is not the currency of energy. Currency of energy is a proton gradient. Energy is equivalent to gradient. If you want to create a concentration difference between one side of the membrane to the other, that's called a gradient. And that is equivalent to energy. It takes energy to make a gradient. And about 1/3 of all your basic energy needs, whatever number of you, 2,000 calories or whatever you need per day, about 1/3 of that is used to make gradients. Alright, so you're making gradients all the time. For example, your nerve signals go using sodium gradient. Transport of glucose uses sodium gradient. So there's a sodium gradient, potassium gradient, different gradients are there. The most common gradient is a proton gradient. For example, your stomach has a pH of 1.5. Where did all that acid come from? It comes from the lining of the stomach. That means the cells in the stomach. They secrete proton from one side of the membrane to the other, and that creates a gradient. And it turns out that ATP is also made from a gradient. So oxidative phosphorylation actually uses energy of oxidation of NADH and QH to create a proton gradient, not to make ATP, but to create a proton gradient because that is equivalent to ATP. And then that proton gradient is used to make ATP. Alright, and that's why, because the unit of energy is not ATP, it is proton gradient. And it takes 4 proton gradients to make 1 ATP. So that means your unit is 0.25 ATP, not 1 ATP. Smallest unit of energy is 0.25 ATP, which is 1/4 of the 4 proton gradient needed to make 1 ATP. So this theory that a proton gradient is used to make ATP So this theory that a proton gradient across the membrane, and we are talking about the mitochondrial membrane, is used to make ATP is called the chemi-osmotic theory. And this was proposed by Paul Mitchell. And he got the Nobel Prize for this in 1978. And that explains why you can have fraction of ATP from these reactions. So all these books that are writing 38 ATP, they should have changed it 42 years ago or 46 years ago when this was actually awarded the Nobel Prize. So obviously it was published much before that. So for a long time we know this chemiosmotic theory, and so there is no need to still have those wrong numbers in the books. So it should be 32 ATP for. So what is this theory? It says that the mitochondrial membrane creates a proton gradient on 2 sides of the membrane. Now, before we do that, let's look at the mitochondrial structure. Mitochondria are organelles in the cell. Remember, the relative size of a cell mitochondria is the size difference between a eukaryotic cell and bacteria. The size of the mitochondria is almost similar to the bacterial cell, and their structure and different properties are very similar to bacteria, and that's why it is believed that mitochondria actually are bacteria that was engulfed by the eukaryotic cells, and that became part of it. So the structure of a mitochondrion is similar to that of bacteria, and gram-positive bacteria, which means it has 2 membranes. The membrane I should be drawing a bilayer like this. So this is one bilayer and this is another bilayer. So this is a gram-positive bacteria. Mitochondria have similar size as the bacteria and similar structure because it has the outer and inner membrane, but there is a difference. So here is the mitochondrion with it has the outer membrane, and the inner membrane is not like this, but it is like this. Well, and then this is the membrane, the bilayer. So it is a convoluted structure that almost occupies, I should draw it bigger, and then on this side also it is bigger like this. So basically the whole mitochondria is full of these inner membranes. So what is the advantage of that? You have more surface area, right? So there is so much of reactions happening in the mitochondrial membrane, all these proteins and different complexes, they have to be in the membrane. This is where all your energy production happens. And so mitochondria are very busy organelles. And all that is happening in the membrane, and so you need a lot of membrane, and that's why it has this kind of structure throughout the mitochondria, the inner membrane. So on one side, then this is this space between the outer membrane and the inner membrane, and the inter membrane space, and the space within the mitochondria is called the matrix. Alright, similar to structure as, let's say, if you are comparing to a bacteria, it will be the cytoplasm and the outside, or the intermembrane space for gram-positive bacteria. So intermembrane space and the matrix, these two names will come up again and again as we study this. And what is outside this? This is the whole cell outside this, right? So this is the whole cell inside. There are hundreds of mitochondria there. So this space is the cytosol. So this whole space is the cytosol. In it there are these organelles. Inside the mitochondria, it is the matrix. And between the outer and inner membrane, that space is called the intermembrane space. Now, the bacterial outer membrane has pores in them. That means there are small openings right here. And these pores allow different things to go in and out. So the pores are quite permeable. They don't have much specificity, they have only slight specificity. They allow most of the things to go in and out. And that means whatever you have in the cytosol, you also have in the intermembrane space. So whenever we talk of intermembrane space, it is almost the same composition as the cytosol because there is free movement through those openings in the outer membrane of the mitochondria. Alright, so we will be talking about intermembrane space, but remember that is the same as the rest of the cytosol of the cell. Yes?
But that would only be for bacteria, right?
What will be for bacteria? Bacteria don't have anything outside. They have only the cells.
Oh, true.
Right? The mitochondria have the cytosol outside. Alright, so here are the different proteins that are carrying out the different reactions. So if we expand the mitochondrial membrane, so just draw a straight membrane like this. But it is not straight, it is convoluted. Just draw it straight like this. So on one side will be the matrix, and the other side is the intermembrane space, which is same as the cytosol, or same composition as the cytosol. In this membrane, there are these protein complexes. That are in the membrane, and when do you have complexes? When it is doing a very complex reaction, multiple enzymes, multiple proteins together form a complex, and oftentimes we don't even know what they are doing. There are so many of them, it is so complicated. So these are called complex 1, complex 2, complex 3, and 4, and 5. So for oxidative phosphorylation, these are the 4 complexes that are creating the proton gradient, and the 5th complex is using that proton gradient to mediate it. So that's how that's the summary of the whole thing, how it works, and we will look at what happens in each of these complexes. So what these do is they take protons from inside the mitochondria and pump it outside. And in order to pump proton outside, you need energy, and where is that energy coming from? It's coming from oxidation of NADH, oxidation of QH2. That oxidation energy is used to pump protons, and it creates a proton gradient. Gradient is equivalent to energy, and that energy will be used to make ATP. So there will be more protons on this side. and less protons on this side, because protons are pumped out, right? So less protons means higher pH, right? People get confused about this. Less proton means higher pH, outside is a lower pH or more acidic. Alright, so the matrix is higher pH, the cytosol is a lower pH because of these proton gradients that are always created. And then finally, these protons are used by this complex, so this is called complex 5, and so it is also called ATP syntax. Not a correct name because ATP synthase is there. It's one of the proteins in there that is making ATP, but it is also a complex of proteins. And when the protons come through this inside back into the cell, back into the matrix, it uses that energy of the gradient to make ATP. So that's how ATP is made. Yes. All right, so we will take a 5-minute break. Yes.
Так собаки росли треба.
Complex 5.
You do the same exact thing.
Over $1,000, bro. Over $1,000. Over $1,000 in your bugging, bro.
I'm trying to fucking study.
So if you want, I can get for you an email. If you bother for someone. $1 fee. Yeah, I don't think no, just do
Bro, you can put in a check-in.
That's what I said. I just gave them a check.
Open the app. Just open the app. Yeah, and it goes to your account number and routing number. Bro, the school still owes me like $50.
Oh, with you? I want to be like that. Are you paying a lot?
I'm figuring out what
You have to be below heavy right now. Oh, actually. Damn.
Oh, like, pull out 50 bucks.
Oh my god.
Oh, next semester I gotta pull out 55.
Like after my scholarship for financial aid, I still paid That's crazy.
Well, the school still owes me $1.5 billion, I swear.
Like, out of pocket.
You're just gonna take out loans for all 4 years? I'm not. Well, you gotta graduate with like $300,000.
350. I already did the math, but I'm looking at 350.
You know the last
Shit, by the time you pay all that shit off, it's gonna be like probably
You ever,
$600,000.
you ever heard of minimum payment? Till the day I die?
That's what my brother is. He pays $50 a month.
Till the day I die, I don't care.
$50 a month.
Yeah,
10 years they paid off for you, yeah.
He's just gonna wait out for 10 years and they're gonna just pay it off for you.
like you run after your dollars. I don't want to be like, ridiculous.
You gotta stop whole crowds. You gotta run out before whole crowds do.
What are you talking about? After this class?
That's a big teacher.
What time is organization?
You guys have your organization?
Is it Andrew stay for that?
That's why I asked you for help. I ended up driving.
And what's he gonna do? Take the
You
train
know I was
back?
gonna leave Andrew in the morning, right? It was like 7:40. And I'm like, I texted Andrew, he's not awake. So I'm like, alright, fuck this. So I'm driving down the E6, I'm about to turn on the highway, and he calls me, he's like, boom, boom, I'm awake. So I'm like, alright. So I went down to his house and I go,
I'll go get a coffee, wait. But Dakshi Membara? You sure?
Yeah, let me get a coffee, bro. Like, I'm waiting for him to offer me a coffee.
it's because you were talking shit about it last time.
Yeah, it was pretty garbage. Why am I supposed to put my own sugar in the coffee? I paid $6 for this tiny latte. Huh? I paid in increments. It's 16 bins. I pay like 4 bins a month.
I think our shit's the same. My shit is also 16, but I pulled out like 10 bins.
A loan?
So I'm only paying
Why?
6.
Why are you paying a loan?
I don't want to pay all that shit.
Why?
Fuck that. That's bad. I don't what they answer. You know what? It's 16 bit.
Yeah, but interest will stack up.
No, I got the interest rate.
Okay. Technology agency? Which one is it?
There's
So it means it gives you 5 minutes.
no. Hold on. There's 2 interest rates. There's the house student one. Interest rate. There's the last one. It's only like 5. Yeah, it was 5 questions. That was enough. That's all I needed.
Yeah, it's only like 5.
It was 5 and 5, so it's about 10,000. I didn't want to take any loans.
It's too early to take interest loans. And imagine, like just imagine, like God forbid, something happens.
Well, no, if you die, your loan's not.
No, I'm talking about like seeing a kid with you in the school.
I'm still going to do that.
Yeah. No, we're gonna pass. We're gonna do this quiz. We're gonna get a D guarantee. Hopefully it's a C.
The school's not saying that much more paying. I'm not repeating the year.
That's ridiculous.
No, if I get B, whatever, it's bad.
No way.
You have to get like 2 days before they do that. It's fine.
No, that's why.
I'm not paying that shit. It's fine. I'm passing biochemistry. I'm not passing. I'm not paying. The school's never seen me again. I'm transferring to a kid.
Yeah, no, because it was time restrictions. Bro, it's so confusing.
You have Fridays off too, right?
Yeah, I think there's nothing on Friday.
There's one of the classes. Is
there really?
There's like 2 of them. There's a Friday off.
No.
I have Fridays off. You know how long it's been since I had a Friday off? The past like 3 years, bro. I have to take Friday off.
But I only had to because Roman A1.
I would say it's gonna feel good, but I just want Friday.
Yo, Mo, what's your face for?
Why do you want that?
You got it.
It's like a Sunday.
Exactly. I wrote that thing about Russia. I think about all of that. I've never done anything like that, and I don't want to. You can seem more interested. What? I got a light saving on Sunday. I want you saying on Sunday. I've been actually 3 hours. I got mine for 7.
What card is that?
I think card. No, that was my.
That's your card.
That's my mix.
Oh yeah, I would think I have my dad's card too. I only use that shit like a week ago. I was like, I opened my wallet and I'm like,
Alright, so this is the overall idea. There are these proteins that help to pump protons to the other side, and then those protons come back in, and that energy is used to make ATP. And as I mentioned before, this is called the semi-osmotic theory, that a gradient can be used to make ATP. So this idea was completely new. No one has ever thought of gradient being able to make ATP, so that's why obviously the person got the Nobel Prize for this. One thing that he showed also is that the synthesis of ATP and the oxidation of NADH or QH2, they are tightly coupled. these are coupled reactions, which means one will not happen without the other. So you cannot just oxidize NADH and not make ATP. If you are not making ATP, then you cannot oxidize the NADH. And to make ATP, of course, you need the ADP and phosphate, so that has to be in the mitochondria, and it has to be making ATP, and then only NADH will be oxidized. So what kind of experiment was done to show that? You take mitochondria, you can isolate mitochondria from cells. There are methods of doing that, biologists will tell you how to do that. So you take the mitochondria and you measure the amount of oxygen consumption. How much oxygen is consumed by these mitochondria, and oxygen consumption means the NADH is getting oxidized. So if you measure the oxygen concentration, if you haven't added any NADH, of course there will be no oxygen consumption. Let's say you add NADH to your suspension of mitochondria, and you expect NADH to be oxidized, but it won't be. So this fact that you are adding NADH but still nothing gets oxidized until you also add the ADP and phosphate. So you need to add ADP and phosphate. Then the oxygen will be consumed. How much oxygen will be consumed? Remember, consumption of oxygen means NADH is getting oxidized. So they added not enough ADP and phosphate, they added a small amount, and so only a small amount got oxidized, and then it becomes concentrated. If you added more, then it will go down all the way to 0. And then you add more ADP. If you add, then more will be oxidized. So this way, depending on how much ADP you add, it will go all the way down to 0. So that means all the NADH has been oxidized. So this experiment proved that the two reactions, phosphorylation and oxidation, are coupled. And the process, as I said, is called oxidative phosphorylation, which means you oxidize NADH and that energy is used to phosphorylate ADP. And the two reactions must be happening together. One thing that they observed is that the mitochondria that you make for doing this experiment must be good quality mitochondria. That means you need intact mitochondria. If your mitochondria that you made somehow got broken, or you are not a good researcher and made a bad mitochondria that are broken down to pieces, then you don't get the full reaction. Or if you take only broken membranes, or you take only ATP synthase, this enzyme can be purified. So you take ATP synthase and add NADH and ADP, add everything, and nothing happens. NADH doesn't get oxidized. Just because you add the right enzyme doesn't mean the reaction will happen. Not only that, not just the purified enzyme, even if you have the membrane, still the reaction won't happen unless you have the complete mitochondria that is not broken, not just pieces of the membrane. And that now we understand why, because if this is the mitochondria to complete the circle, you need this gradient from the two sides. If your mitochondria is broken, like if there's a break here, then all these protons will come from here. So it is the broken pieces of membrane will not work, purified enzyme will not work. You need intact mitochondria so that the proton gradient cannot dissipate through these broken parts. It has to go through this complex in order to make the ATP. And that's why you need the intact mitochondria for this experiment. They did the same experiment and of course if you don't add the ADP, nothing happens. And then instead of adding ADP and phosphate, they added other compounds. One of them was dinitrophenol, 2,4-dinitrophenol. And when you add this, the NADH gets oxidized right away. So you haven't added any ATP, any ADP or phosphate, but still all that energy is gone because the NADH is getting oxidized without making any ATP. So that means you have uncoupled. Remember, these two reactions are coupled. You have uncoupled by adding this strange molecule called dinitrophenol. And so dinitrophenol is called an uncoupler. And what does the dinitrophenol do? It takes the proton from this side and brings it through the membrane to the other side. That means it dissipates the proton gradient, and so you are not making any ATP. Instead, all the proton gradient is used up. So, for all the business-minded people here, or all the pharmacists here, or would-be pharmacists, that give you an idea of about making a drug with this, right? What kind of drug will it be? If you are oxidizing all the food and not having to do the exercise, you are just sitting there and all your energy is dissipated. And so you need to eat more to make more NADH, and still you are not making ATP because all the energy is going down. So obviously you are losing weight, right? You are burning calories without exercising. Isn't that good? Right?
Yes.
You have to do no work and you can burn all the calories you want. No exercise, just sit and you can burn all the calories you want.
I'm watching Honey Bird.
Listen, what to stop, buddy.
Is that true or just wishful thinking?
I feel like it would kill you now.
It's not wishful thinking. It is a drug. It is a drug that was actually marketed and then taken off the market right away because people were dying. Why were people dying?
Because you don't make any ATP.
Because what?
You don't make any ATP.
So give them a small amount, don't give too much.
Wait.
Yes. No, there is no inhibitor here. This is not an inhibitor. This is just dissipating the gradient. And so what will happen? When does the energy go? I mean, the energy cannot disappear, right? The energy
They overheat.
said that these people are overheating, not doing any work, the whole body gets heated up. Yes. Much more. This is similar to a substrate cycle. You are creating a substrate cycle by doing this. So that means you are making your mitochondria leaky intentionally by adding these uncoupler. And again, this is another thought that people have, that all these hibernating animals, they also probably get energy by making their membranes slightly leaky. Right? The point that you said, you will not make any ATP, but you can control how much ATP you make by adding these uncoupler in small amounts. But of course, you cannot sell this uncoupler anymore. It was taken off the market right away because people started dying without doing any exercise. Their body getting overheated. Yes.
Wait, I'm sorry. When was this?
Google that.
Oh, word.
So yes. So as a pharmacist, you need to know when this happens. Yes.
Shouldn't the drug be tested and shouldn't we find out how
I don't know. You're the pharmacist. You should tell.
That's recent.
How did they get into testing? They could have drug that kills you.
Oh, he's drawing out the actual penetrate.
Oh, you didn't do this?
I do this also. I'm doing it in the spring, October.
All right, so this is the molecule called the uncoupler. How does it work? How does it uncouple the oxidation and phosphorylation? So this is a phenol. Phenols, as you know, are acids, right? Like it's probably weak acid, but they are acids, just like tyrosine. So phenols can ionize, and the reason you choose this is the pKa of this is right where you want it to be for all these things to happen. Even though there is a pH gradient, there is protons, but there will be a certain pH associated with that. And if the pK of your compound falls in that range, then this will ionize. And this ionizes in the membrane. So if this is your membrane, and there are more protons on this side than on this side. So this thing will ionize at a lower pH, sorry, at a higher pH. So any acid will ionize when the pH is high, and so this will become the phenolate ion. Now, phenolate ion, of course, is ionic. It has charges, and charged things don't go through the membrane, right? But these nitro groups are positioned in such a way that they are at the ortho and para position from this negative charge, so there will be resonance, right? You can draw many resonance structures for this negative charge forming a bond here, and then they are shared by this oxygen and by this oxygen. So you can draw many resonance structures in which the negative charge is delocalized. Delocalized by resonance, and so you don't have a high charge density on that molecule. So there is a charge, but charge is distributed over all the carbons and the nitrogens and oxygen. And because the charge density is low, so this can cross the membrane. So that is important for an uncoupler, that it should be able to cross the membrane even though it is charged. And when it is not charged, this is aromatic. And so it is hydrophobic and can cross the membrane. So this molecule or a uncoupler should have the property that it should have its pKa in the right range, such that it will ionize, and then the ion can cross the membrane, and unionized form can also cross the membrane, and then it will act as an uncoupler. So let's write the whole thing as A, and this one as HA. Remember, this is a weak acid, so HA and A. So if you have this A minus on this side, if you have A minus on this side, it will combine with a proton to give you HA.
But then HA crosses.
On the intermembrane side, there is more proton, so this gets protonated. On the matrix side, there is less proton, so it gets deprotonated. So this HA then crosses the membrane and comes to this side. And here there is less proton, or the pH is higher, and so this deprotonates. Let me write the opposite, H plus. And in the deprotonated form, which is this one, the anion, it has a charge, but it still can go to the membrane because the charge is delocalized, so this can cross the membrane from this side. So the uncoupler molecule comes to the intermembrane space, picks up a proton, becomes the protonated form, crosses the membrane, loses that proton, and again goes out, brings another proton. So every cycle it is bringing a proton from outside to inside, and that's how it is dissipating that proton gradient. So that's how the uncouplers work, yes.
How is HA crossing over the membrane? You said that it's-
Because it is aromatic.
Aromatic.
So this, because of the hydrophobic ring here, it can cross the membrane. So the hydrophobicity and the hydrophilicity should be at the right balance so that it can go through the membrane. You cannot just take any molecule that is aromatic and also has these nitro groups on them. Nitro has a charge, aromatic group is not charged. So it should have the right amount of charge and hydrophobicity so that it can go through the membrane both in the protonated and deprotonated form. If it can do that, those are called uncouplers. Alright, so I'm going to erase this.
Oh, you're not called for Canada. That fixes me.
Alright, so these different complexes that are there. Alright, so there are these 4 complexes. If you draw this, 4 complexes that make the gradient, and complex 5 uses that gradient. Alright, so complex 5 is ATP synthase, yes.
So you said that the protonated version of the uncoupler can cross the membrane, but what about the deprotonated one? Can that also cross the membrane?
Yeah, I just erased that. The deprotonated form has a negative charge that is delocalized and it is stabilized by the nitro groups by resonance. And resonance means delocalization. That means the charge is not completely on that oxygen, it is shared by all the oxygens in the molecule. So the whole molecule is sharing those charges, and that decreases the charge density, and so it can cross the membrane. So it is charged but not a high charge density. And so all molecules that are charged cannot cross the membrane, so this is the ideal one. Or there are other uncouplers also that should fall in the right range of pK, and the charge should be such that it can also cross the membrane. Alright, so in these different complexes, and once again there are 4 complexes that make the gradient, and the 5th complex uses the gradient to make it. So the complex 1 will be oxidizing the NADH. Now, oxidation, as you have studied in general chemistry, can also be viewed as loss of electron. So NADH is oxidized and oxygen is reduced. So this is the overall reaction, that NADH will be oxidized and the oxygen will be reduced. But it is not happening right away. The oxygen, NADH is not really reacting directly with the oxygen. That's the overall reaction. And why is it not directly reacting with oxygen? That I explained before, because if it reacted in one step, then you are going to make only 1 ATP, right? Or all that remaining energy is going to get you heat energy only. So you don't want the reducing power of NADH to directly react with oxygen. So oxygen comes after multiple steps. In the final step, it will be oxygen reacting to give you the energy. And in every step, you are going down in the reduction potential. So that means something is a strong reducing agent that will give you more ATP, right? So or more energy when it is oxidized. But you don't want that to happen in one step. Instead, you are starting from here, it goes down to here and then to here. So it goes in multiple steps. And these are the different complexes Within a complex also, the steps are not just one step. As I said, it's a large complex of multiple proteins, and there are many different metal ions also involved, so we are not going to study all that, but just understand that it is happening in steps, and it is getting oxidized. So at the end, then there will be the transfer of electrons. So electron is transferred from the NADH. From NADH, the electron is transferred to oxygen. Or once again, oxidation is loss of electrons. So NADH loses electron, and oxygen gains electron. So that whole process through these multiple steps is a transfer of electron from NADH to the oxygen after all these different steps. So this whole process is also called the electron transport chain. So oxidative phosphorylation happens by electron transport chain, and at each of these steps the reduction potential goes down, or reduction potential is same as or equivalent to energy. You can also, instead of plotting the reduction potential, you can plot energy. So the energy will go down as it goes from NADH all the way to oxygen. And as the energy goes down, then it is releasing that extra energy to make the proton gradient. So if complex 1 is here, it will transfer its energy to another complex, which is complex 2. Complex 2, complex 3, there isn't much of a change of energy. So complex 2 doesn't really make any ATP, doesn't make any proton gradient because of the potential difference, reduction potential, whichever way you look at it. Difference of oxidation potential, opposite will be reduction potential, and they are all equivalent to energy. So when you are plotting, you can plot reduction potential or oxidation potential in the opposite direction, or just plot it as energy. Alright, so high energy to low energy. Complex 2 is actually, as I mentioned when we did the citric acid cycle, that the succinate dehydrogenase is the only enzyme of the citric acid cycle that is also part of the oxidative phosphorylation, and complex 2 is that one. So this is the succinate dehydrogenase. So what does it supply for oxidation? The QH2. Remember, this is the step in which QH2 was formed. And complex 1 oxidizes NADH. So the electron goes from NADH to QH2. So that means NADH becomes NAD, and that hydrogen is transferred to Q, which now becomes QH2. So you can, once again, you can look at it as a graph of reduction potential, oxidation potential, or you can look at it transfer of hydrogen, just like transfer of electrons. Or someone can say it is also a transfer of hydrogen. The hydrogen goes from NADH and is transferred to Q. So you are making QH2 from the complex 2. Succinate dehydrogenase is also making QH2. Remember, succinate dehydrogenase in the citric acid cycle, you made QH2, and that enters this electron transport chain or the oxidative phosphorylation process at the complex 2 stage. And so it bypasses complex 1, it just directly enters here, and all the NADH starts with complex 1, and the hydrogen is transferred to QH2. So at the end, whether it's coming from succinate or coming from all the NADH, your product is QH2. So when QH2 is oxidized, you are starting from here. So you did not start from this point, and so NADH gives you, remember, 2.5 ATP, and QH2 gives you less, and gives you 1.5 ATP for QH2. And that's because QH2 is entering this process in the middle, and NADH is entering at the complex 1 stage, which converts NADH to energy, and the energy is used to make proton gradient, and the hydrogen is transferred to make QH2. Eventually, what will happen to that hydrogen? Either it needs to be oxidized or it can contribute to the proton gradient. So there are two ways you can contribute to the proton gradient. One is to use the energy. It's going down from this energy level to this energy level. So that difference in energy is used to pump protons from one side of the membrane to the other. That creates proton gradient. The other way to make the gradient has to do with this hydrogen. In this step, you are not using the hydrogen of NAD, because that hydrogen is going to QH2 to make QH2. Eventually that QH2 will not keep all that hydrogen, but that hydrogen will again contribute to the proton gradient. So QH2 will eventually give you proton gradient just from this hydrogen in the formula. Plus, as you are oxidizing it, it's going from high energy to low energy, and that energy is used to pump protons. So every complex then pumps proton to the other side and contributes to the gradient in two ways, either by pumping protons or by releasing the hydrogen from its formula, if it has a hydrogen. Of all these, the complex 2 doesn't really contribute anything to the proton gradient because it is only contributing QH2, it is supplying QH2. It is not, the difference, as I mentioned, when it goes through complex 2, the difference in the potential, in the oxidation potential or reduction potential or energy is almost a zero for complex 2. And so it doesn't contribute to the gradient, but it provides QH2 that will later give you energy. Yes.
Going from 1 to 2 is barely a difference, or from 2 to 3 is barely a difference?
I can give you all the numbers. So let's say you go from NADH to Q. When it is transferred from NADH to Q, the delta G for that is minus 60. When you are transferring from, so this is complex 1. Complex 2 is going from succinate, the hydrogen is transferred to Q. Right, that was in the citric acid cycle. And that delta T for that is close to 0, is about 2. So 2 kilojoules is not sufficient to pump any protons or do anything. So actually, yes, this is minus 60 and this is minus 2. So almost 0. And then complex 3, which we haven't studied, the QH2 will transfer its electrons to another molecule called cytochrome C. And that has a delta G of minus 35. And then complex 4 will transfer the electron from cytochrome C to oxygen. So these are the 4 complexes. The NADH doesn't react with oxygen directly. It first transfers it to Q, loses some energy, and that energy is used to pump protons. Then succinate transfers it to Q, that is happening in the citric acid cycle. So more QH2 is produced, and that doesn't contribute anything to the proton gradient, but it contributes QH2. All that QH2 coming from this as well as this one will then transfer it to cytochrome C, another small molecule. And that process also has delta G that is negative, so that also is used to pump protons. And finally, cytochrome C is directly oxidized by oxygen, and this has 110 kilojoules. So all these negative ones, complex 1, 3, and 4, will be used to pump protons. Yes?
So what exactly does complex 2 do? You're saying that the substrate is transmuted to doesn't that happen in the citric acid cycle?
That is the protein that is happening in the membrane. The citric acid cycle, remember, that was the only enzyme that is in the membrane, and that is the same as complex 2. Yes, yes. Part of means this is the only step of the citric acid cycle that is in the membrane, because remember Q is in the membrane. Because of that isoprene unit, it is membrane soluble, so all that is happening in the membrane, so that is the only enzyme that is in the membrane, and that contributes Q, so that is included in this as a complex 2. If someone doesn't want to include that, then it doesn't exist, but you get QH2 from the citric acid cycle.
So does enzyme 2 not contribute to the proton gradient, or it just contributes like barely anything?
It doesn't contribute directly to the proton gradient, but contributes QH2.
Okay.
And in the next step, the QH2 will transfer the electron to cytochrome C and give you minus 35 energy. So it is contributing a reducing agent or a reduced compound that will give you ATP, but it is not pumping any protons based on energy difference. Now, cytochrome C does not need the hydrogen. As you see, QH2, when it goes to cytochrome C, it does not need the hydrogen because it's a metal ion, and metal ions have oxidation states like copper 1, copper 2, iron 2, iron 3. So when you are reducing metal ions, you are not adding hydrogen. When you are reducing an organic molecule like Q or NAD, that hydrogen is part of that molecule. It becomes part of the molecule. But when you are reducing metal ion, the hydrogen has to be released. So in this step, these two hydrogens are released as protons. If you write the formula, write the equation, those will come out as protons. So the QH2 also contributes to the proton gradient just based on its formula, because the hydrogen is not bind or form a bond with the cytochrome C, they are released as protons. So there are two ways in which you get proton gradient. One is using these energies, this one, and this one, to pump protons, and coming from the formula itself, because this is reacting with cytochrome, transferring the electron to cytochrome C, and in the process it doesn't have to transfer the hydrogen. So the hydrogen is eventually contributing to the proton gradient. In complex 4, the product is transferring the electron to oxygen. So what will oxygen become?
It's 1051.
Yes. All right, 1051. So what will oxygen become? We'll do next time. All right. So once again, on Thursday at the end, we will have. And anyone who doesn't want to take the quiz, that's fine. Somebody have a good day, but still want to take the quiz.